to answer those questions. Okay, this is it. So today is Monday. And that's 31st. And these topics are mostly in 5.6 and 5.7. And we talk about it briefly. You don't need anything else other than these notes. So what is inverse trigonometric function? Inverse trig functions, trigonometric metric functions. I'm going to talk about one of them in full details. Then I give you the formula for the rest. Okay, the most famous one or popular one is inverse sine function. Inverse, okay, inverse sine function. I've seen this type of functions in your pre-calculus. So just remind you the definition that we use over there. So recall that. Okay, recall that the inverse notation first, the inverse sine function. Inverse sine function is denoted by, is going to be denoted by, that's it, y equal to sine inverse. It's not a power, it's just a name. Okay, if it's happened to be to the power -1, they open up the parentheses and then raise it to the -1. So when you see this one, it's just a name, sine inverse. In some books, very bad, but even in your book, sometimes they use this notation, arc notation. Arc notation is good for the trigonometric function, trigonometry, not for calculus. I'm not going to use it, but this is the one that we are going to use, and is going to be defined, and is defined by, just as you do it with any other inverse function. The definition is going to be, if you want to know anything about the sine inverse of x, you have to go to the other side. So it's going to be if and only if x is equal to the sine of y. That's the definition of a sine inverse. You switch. Okay. So in this case, we know everything about the sine, but there are a difficulty that you cannot do this one for all the domains. If you like, you know that the sine domain of the sine is going to be all real numbers, and it's going to be periodic between 0 and 2 pi. That is usually we have. But in order to make sure that the sine inverse is a function, as you did it in pre-calculus, you restrict this one into this domain. So this is true only where there are many choices, but this is because of the calculus that we are going to assume that this angle is going to be only between -pi½ and pi½ and then the sine of the pi½ is going to be 1. So in this case, you get the x to be between -1 and 1. So this means that the domain of the inverse function. So therefore, the domain of the inverse function is going to be a closed interval of -1 and 1, and the range of the inverse function is going to be between -pi½ and the pi². So if you want to use any angle in the problem related to the sine inverse, you must make sure that your angle are going to be in this, okay, this is it. So this is going to be -pi², and this is going to be a +pi². So you can only pick the angles in this, okay, in this portion only. And the reason that we use this one in calculus is in the first quadrant and the last quadrant, the cosine is always positive. You see, this is going to be the cosine. Cosine is always positive, because in most of the problem in calculus, you arrive at the cosine squared, and you have to take the square root. If you want to take the square root, you must make sure you know that when you take the square root of, for example, radical x squared, the result is the absolute value of x. But in this case, always, you see, if you want to have something like, you want to take the square root of a cosine square of y, now you know that this is always equal to the cosine of y. Because you have to use the absolute value, you know that you have to use the absolute value, but you can drop the absolute value. This fact is going to be used quite a lot in calculus too. So that's why there are other possibilities in when you do it as in a course of the trigonometry. But in calculus, this is the reason. And you pick this one to be begin negative pi half and the pi half. Again, these are probably has been discussed for you in your previous pre-calculus course. Okay, so this is the function that we are going to be interested in. If you want to get any value of this function, you can use your calculator. So we are interested in the derivative of this function only. So let's see how we're going to differentiate it. So note that if y is equal to the sine inverse of x, and then if you want to differentiate it, if you want to find the y prime, okay, if you want to find the y prime, it's just a proof. You can memorize it, anytime you forget it, but this is the way we do it. You see, if you want to find the y prime, you won't get anything from here because you don't know anything about it. So what you have to do is you have to get the definition. You just put the definition of the sine inverse. You see, this is the sine inverse of x. As we talk about it, we can switch it. You switch it into the x equal to the sine of y. You see, now differentiate. If you differentiate both sides with respect to the x, if you differentiate it, derivative of x is equal to 1, equal to sine of y. Remember implicit differentiation that we did? Or a composition of two functions. It's like sine of u. Derivative of a sine would be cosine. So it's a cosine of y, but you have to multiply, remember, by y prime. Because it's implicit differentiation or a composition of two functions. Now we can solve for y prime. So y prime would be 1 over cosine of y. Okay, but we would like to write everything in terms of the x. So what we have to do is a little bit of trigonometric identities to get the cosine of y. We say, oh, note that. Okay, note that you know that the cosine square of y, particular identity, is 1 minus sine square of y. But the sine of y is equal to the x. So this is going to be equal to the 1 minus x squared. Okay, now take the square root of both sides. If you take the square root, cosine square of y, and this is going to be the square root of 1 minus x squared. But remember, we arrange it so that cosine square of y to be positive all the time. Say that cosine of y is positive. Okay, if you like, but so the conclusion is going to be you get cosine of y is equal to the square root of 1 minus x squared. So if you go back and put it over here, you have a formula. Okay, if you go back and substitute it, you get the fact that the y prime is equal to the 1 over square root of 1 minus x squared. So, but remember, y is sine inverse. So you have a formula. Okay, so the conclusion is going to be, I write it here, then I repeat it in the next page. Derivative of a sine inverse of x is going to be 1 over a square root of 1 minus x squared. That's it. Very popular formula for calculus 2 and for the application problems. Okay, I just proved it to see how you get, you get this one. And we are going to do this one for all the other inverse trigonometric function, but I did this so, you can, if you want to do it, you can do the other one yourself. Okay, so this is the key formula that we need to know. It's the derivative of sine inverse 1 over radical 1 minus, okay, 1 over square root of 1 minus x squared. So let's make it official. Any question? So we proved something, so we can write down as a formula, as a theorem, and this is how we are going to use it for the test. Okay, so this is the theorem. So what is the theorem that we proved? So we proved, I write it down in two parts. Part one, we just proved that the derivative of a sine inverse of x is simply 1 over the square root of 1 minus x squared. That's one formula that you have to bring it. The other one, of course, as usual, if it's not sine x, sine something else, so we have to apply the chain rule. So the second part is going to be if, as usual, if u equal to the u of x, okay, u equal to the u of x is differentiable, you can apply the chain rule, is differentiable. It's going to be differentiable. Then this time, if you want to find derivative of sine inverse of u, remember it's a composition of two functions. Outside function is sine inverse, which is this formula. Inside function is u. Chain rule. Derivative of the outside is 1 over the square root of, okay, 1 over the square root of 1 minus u squared, but you have to multiply by u prime. So, or this is the way we memorize it. Derivative of the sine inverse of u is simply u prime over the square root of 1 minus u squared. So this is going to be the main formula that, you can memorize it and use it all the time. Okay, so, we memorize this one. If you replace it by x, your prime would be 1. So 1, 2, this is what you need. But you know that any formula in case of the derivative, we can switch it into the notion of the indefinite integral. So this is going to be equivalent form for the integration. Equivalently. So this first one would be changed into the integral of dx, or 1 over the square root of 1 minus x squared dx. So this means you are interested in a function whose derivative is 1 over radical 1 minus x squared. So that function is sine inverse. So that would be sine inverse of x plus c. And you're done. And this would be changed into the u substitution. So that's going to be du, if you like, or 1 over the square root of 1 minus u squared. The du, it's the same thing. It's going to be sine inverse of u plus the constant c. So this is the 4 formulas that you need to know for the differentiation and the integration of the, okay, I changed this integration a little bit for you, but this is all we need, okay, we need to know. Okay, any question? Now we give you example, a couple of, differentiation, a couple of integrations, and then you're done. And this is going to be our sine inverse. And then we show that the cosine inverse is very similar to the sine. You don't need to memorize it. You don't need that. Then we get to the tangent. Okay, so let's get practice. So your first job is going to be the following. Differentiating. There are only 2 possibilities for differentiation. So this is it. Find the derivative of each function. Find the derivative. Any question? Find the derivative of each function. Couple of easy case. Okay, the first one. The first one is going to be something with the product. You did it with the product rule for the natural log exponential function. Now we do it for this type of function. For example, f of x equal to 3x to the fourth times sine inverse of x. It's the one that you don't need the chain rule. You just realize that it's a product of two functions. So the first function is 3x to the fourth, so it's going to be your first function. And the second function is sine inverse. So you have to apply the product rule. First, second. So derivative of the first times second plus derivative of a second times first. That's it. Okay, so this is going to be a solution. F prime equal to derivative of the first one. 4 times 3, 12, 12x cubed. 12x cubed. That's the first one. Times that by the second one, sine inverse of x. Plus derivative of a second times first. Sine inverse. Sine inverse, remember, is 1 over radical 1 minus x squared. That's it. That's the derivative of a second, but you have to multiply by the first one. Multiply by the first one, 3x to the 4, plus the constancy. There is nothing to simplify. You just multiply this, you write it down in this form. So f prime of x is going to be equal to 12x cubed sine inverse of x plus the top would be 3x to the fourth, the square root of 1 minus x squared. I'm sorry, there is no c here. And that gives you the derivative of the function. There is nothing to be simplified. Remember, don't waste your time. You cannot simplify this one. This is the final answer. Only if there is something here, you can simplify it. Okay, so that's a kind of the product rule and the inverse sine function. Again, is a product of two functions. If of the first one, 12x cubed times the second function. Plus if of a second function times the first. The second function is sine inverse. So the derivative of a sine inverse is 1 over radical 1 minus x squared times the first one, and then you're done. Okay, that's a case one. Any question? Case two, the one that you need chain rule. Something like a g of x equal to g of x equal to the 5 sine inverse. Okay, sine inverse of x squared. You see 5 is a number, so you don't need the product rule. But this is not sine inverse of x, it's sine inverse of something else. So you imagine that this is going to be u. So you know that you have to use this formula. Derivative of a sine inverse of u, which is going to be u prime over radical 1 minus u squared. As usual, you know that when you use the chain rule, you have an extra term. That extra term is going to be your u prime. Okay, so this is it. G prime of x equal to 5 is a number. 5 is a number. If you have a sine inverse of u, it's going to be 5 times. Copy that formula. You see, do the bottom one first. The bottom one is 1 minus whatever you have here is squared. X squared is squared. That's the bottom. The top is u prime, derivative of x squared, which is 2x. Okay, 5 is a number, you just repeat it. So sine inverse, just do the bottom first, is 1 minus u squared. 1 minus x squared squared. But since it's x squared, you have to multiply the top and u prime, 2x. Now you have to do the algebra. You multiply these monomials together. So g prime of x is going to be equal to 5 times 2, 10, 10x. Okay, denominator 1 minus x squared would be x to the 4th. So you have to do this simplification for us to get the final answer. Okay, that's the derivative of the sine inverse of other than the x. So again, as soon as you get the x squared, just remind yourself, it's a composition of two functions, sine inverse and the x squared. The derivative of a sine inverse is 1 over square root of 1 minus u squared. So you do the bottom one first, 1 minus whatever it is squared on the top, u prime. Don't forget the u prime. So these are the only possibilities that you are going to have for the differentiating these functions. Any question? So that's a differentiation. Integration, you have lots of fun over there. For the integration, we have another technique for integrating these functions in calculus too. But this method is much easier. So what is the possibility for integrations? Example, and we would like you to evaluate each integral. Evaluate each integral. Okay, you know that your formula is only this one, integral of, let's say, du or dx, 1 minus u squared is simply sine inverse of u plus c. This is your formula. So let's take the first one. Integral of is going to be dx. Okay, dx. Then what? Then a square root of 1 minus 4x squared. You see, this is the one that you have. Now, the only things that you have to be concerned is this is not x squared. If it's going to be x squared, you get the formula right away. But it's something else. So you have to use the u substitution. For the u substitution, you have to do a little bit of a mini substitution method to change it into the 1 minus u squared. Okay. So what you are going to think about it is you can think about the 4x squared as you say, if you think about 4x squared as 2x all squared. Okay. So this means your u is 2x. Then you do the substitution method. Okay. So this is the only thing that you have to be concerned with. So this is going to be your solution. We are going to rewrite it first. So you rewrite it as dx, a square root of 1 minus 2x all squared. So you have to do the substitution to make it into the radical 1 minus u squared. Okay, so what you're going to do is you have to take the u to be 2x. Okay, the target, remember, is 1 over radical 1 minus u squared. So you find the du, the derivative of the 2x would be 2 dx. Then you find the dx. So the dx would be, okay, dx is equal to the du over 2. Just a substitution method that you did before. So you have to do it for, it's not going to be straightforward. So you go back, substitute, and the target is going to be du over radical 1 minus u squared. Okay, just going back, substituting here. Okay, so and this is it. I rewrite it here. So I have the dx. You can do it right away, if you feel comfortable. So this is what I have now, 2x all squared. So substitute. If you substitute, this is going to be a square root of 1 minus, remember the 2x is u, it's going to be 1 minus u squared. But what is your dx? Your dx is du over 2. There's going to be an extra term, 1/2. You pull out the 1/2, it's going to be 1/2 integral of, and that would be the du radical 1 minus u squared. You see, you arrive at the target that you needed. So this is going to be 1/2. This is going to be 1/2, and this is going to be sine inverse of u plus c. But what is u? U is x squared. So the result is going to be 1/2 sine inverse of x squared plus the constant c, the final answer. For the integration, this is your job. It's not going to be a straightforward one because they put something here. You can do it right away. The short form is going to be the one that we did before, really. U prime would be 2. So you can create the 2 here, divide by 1/2, and do it a shortcut that we did it before. But now we want, we want to practice to be able to take care of these type of integrations. Okay, any question? Remember, there is another method, we call it trig substitution in calculus 2. On this, this is calculus 1. So don't try to use it if you have seen it somewhere else. Okay, this is straightforward. That would take time, even if you want to do it. But this method is much, much easier. Just, a mini substitution that can be changed into a shortcut in future. So if you see other methods in other books or somewhere online, don't be surprised, but this is calculus 1. And this is a quick method. But any other method that you'll be able to get it through, I accept it. But this is very easy method. Okay, that's a type 1 for the integrations. Any question?
Yeah, wait, so how did 4x squared become 2x squared and we didn't do like the antiderivative since we are integrating? I'm a little confused on that.
You see, you need to have 1 minus u squared here, okay? So this is your u squared. Since this is your u squared, so your u would be what? Your u would be 2x. So you take your u to be 2x to just make sure that you are going to be changing to the 1 minus u squared.
Right, but how did it become 2x? That's where I'm a little lost.
That's it. 4x squared equal to the u squared. What is u?
Oh, okay, sorry.
Oh, the other way around. Yeah, no, that's it. Okay. So, if maybe this is 5x squared, it's going to be 5, don't be surprised. You get radical 5x, for example, in the problem in your book. Yeah, this is the way we guess that we need this to be u squared. Take the square root. Then make sure you get the du here when you substitute. Some people, they miss the du. Then go back and switch it to that one, and then you're done, really. If you are going to be in calculus 2, just for your information, this is the way we expect you to do it, a shortcut, if you like you did it for the other problem, you see. This is going to be a shortcut that you do in future. If you do calculus 3, this is the way we do it quickly. Remember these problems, I just rewrite it for you. So that's going to be 1 minus 4x squared. You have to rewrite it again. So that gives you the 1 minus 2x squared. Okay, the dx. Now you say, oh, this is going to be u. Remember, when you do the chain rule, if you take this one to be u, so you have to pair the u prime and the dx together to make it du. Remember the du? Du is what? Du is u prime dx. So if you take the u to be 2x, u prime would be 2. So you need a 2 on the top to pair these two together, and you get your du. So to create the 2 on the top, as I did it before for you, it's going to be 1/2. You divide by 2, and you multiply by 2. You see this one? And that would be 1 minus 2x all squared. So what do you have? If you call this one u, you have the du on the top. So you have du over radical 1 minus u squared. And according to the definition, this is exactly the derivative of a sine inverse of u, which is 2x plus c. See? It's maybe you do it in future, or you can do it now if you can match them together. Okay, in this method, you have to pair the u prime and the dx together. But it's calculus 1, and be played safe if you like. But that's very good. It's also in your book. The way, in this method, you have to pair the u prime and the dx together. U prime is 2, so for pairing, a 2 is missing. So I'm going to create the 2, divide by 2, and multiply by 2. So you already got the du on the top. So this is a 1 minus u squared, and you know that this is simply integral of a sine inverse. Okay, so that's a type 1. But there is another type. This method is applied to all the trigonometric functions. So we stop here and discuss it. And we get this one through for the rest of this section. You see, I gave you a remark here. This remark is important. In this group of the problems, you see, you need to start with the 1 here. Look at the formula. 1, 1, 1, 1. But in the actual problem, they don't give you the 1. They give you something else. So look at this one. They give you this one, for example. It's going to be integral of, you have the du or the dx, doesn't matter. See dx. And they give you a squared minus u squared, a number other than 1. Okay, x squared for the time. They give you 9 minus x squared, 4 minus x squared. Remember that you can use only the sine inverse formula if this is 1. When it's going to be a squared, you have to do a little bit of algebra. You have to normalize it. You have to factor out the a squared to make this one to the 1 minus x squared over a squared. Then continue. You can do this one for any problem or every problem, or you can use this formula that we're going to give you. If you bring the a out, and then you do the u substitution, you will change it into this form. You see, if you factor out the a squared, that gives x squared over a squared. So your u would be x over a. So this would be the formula. You better memorize this, okay? It's going to be sine inverse of x over a plus the constant c. You see x over a because you factor out the a squared here. So if a is equal to 1, that's simply sine inverse of x. Let's go on anything else, you already prepared for it. So, and similarly, if it's going to be u substitution type, it's going to be du over radical a squared minus u squared. It's the same thing. It's a sine inverse of u over a plus c. So it's a matter of algebra. If you don't want to do this one, you have to do it for all the problems. You factor out the a squared, but it's very easy to memorize it and to be able to apply it. So the question that we're going to get in the case of the sine inverse integration, or doesn't matter, tangent, always, it's going to be a squared here. So we want to know how you handle it. Okay. So there are 2 possibilities for this one. I give you both of them, then we're done with the sine inverse. Any question? So make sure you know the difference. You can only use the sine inverse formula if it starts with the 1. If it's going to be start with something else, you have to factor it out. You have to factor out a squared to be able to do it. If you now simplify it, that gives you the final answer. So whatever number is here, you call it a squared. You take the square root to get the a. So if this is 4, this would be 2. If it's 5, this would be radical 5. If it's going to be 3, it's going to be radical 3. So don't be surprised and don't use any decimal numbers. So this is the actual integration, and this is the main reason that you study this section. So this is the one that we are going to be interested in for integral. So we want to evaluate each integral. Each integral. 2 possibilities. You see, I just give you both of them together so that you know it. 2 possibilities. Look at this one, the first one. Integral of dx square root of 16 minus x squared. This is the first one. Second one, integral of dx, okay, square root of 16 minus 9x squared. This is the most general one that you may be given. Okay. So the first one is of the form of a squared minus x squared. You realize that you have to use the sine inverse. You see, this is x squared. If it's going to be x squared, you don't need any substitution method. So we can all substitute and get this formula. A squared is 16, so a is 4. So this would be sine inverse of x over 4 plus c, and do that. Okay, it's of the form of 16 minus x squared. It's very easy to identify that that's going to be a sine inverse type. Okay, it's a sine inverse type. A squared is 16, so a is 4. We get a positive square root only. These a's are positive. Okay, it's not going to be positive, negative 4. So that would it. Now, what is going to be, this is the most general one. You see, for this one, this is 16 minus u squared. Okay, a squared minus is not x squared, it's u squared. So what you have to do is, you have to do the u substitution. To change this one, u would be 3x. You substitute, you arrive at radical 16 minus u squared. Then we can apply this formula. Okay, so two different cases, and one of them would be given to you. The first one, you're just changing the a. A is 16, a squared is 16, so a is 4. Sine inverse of x over 4, done. The second one, this is not x squared, it's 9x squared. So you have to use substitution. You take u to be 3x, you change it to the 16 minus u squared. 16 minus u squared, and use this formula, and do that. Okay, so let's give you the solution of both parts. And it's the same for the tan inverse. Okay, so this is it. Solution. Solution for the first part. That's it. The first one was integral of dx square root of 16 minus x squared. You don't need your substitution. Remind yourself that a squared is, just for your information, a squared is 16, so my a is equal to 4, and the formula was sine inverse of x over a. X over, what is a? A is 4. X over a plus the constant c, and you're done. Okay, because of the x squared here, just normalize 16, we say. Normalize it means you factor it out, you take it out. So that's the first part. Any question? The second part, more involved. The second one is this one, dx over the square root of 16 minus 9x squared. You see, since this is 9x squared, you can do it if it was 16 minus x squared. So you have to use the u substitution to take care of it. You rewrite it. It's a dx over the square root of 16 minus 3x all squared. Now do the mini u substitution. Take u to be 3x, u to be 3x, du, derivative of 3 dx. Find the dx. Dx would be du over 3. Go back, substitute. If go substitute, you get this one. Okay, so substitute here. So that gives you dx. I just repeat it. You can do all of them right away if you don't mind. Substitute. You start for dx, it's going to be du over 3. And this is going to be 16 minus u squared. Nothing to simplify. You have a third, you take it out. 1/3. You see, you get back to the first part. Du 16 minus u squared. You see, you change this one into the u squared. Now for the 16, you know that. So this is going to be equal to, again, remind yourself that the a squared is 16. So your a would be 4. So this would be 1/3. Okay, a sine inverse of what? Of u divided by a, which is 4. And the constancy, you have to substitute for u. Your u is 3x. So this is going to be,
Is it valid if we write arcsine instead of sine to the -1.
I don't like
Does-
it. You can write it.
Okay,
It's
okay.
it's not equivalent. Okay.
Okay, okay.
Because you know that when you write the arc, there is going to be a difficulty for the notion of the functions. You know, those when you solve the equation in trigonometric function, you know that you have a special solution and you have general solutions. When you do it, remember, you have the arc sign with the capital A and the A, you know. But anyway, you can use it, you know, officially you can use it. But I avoid it in calculus, okay? And we don't use the arcs, but you can do it. Fine, we don't mind.
Okay.
Okay, so that's going to be, so what else do we have to do? We have to just substitute for the u, which is 3x. So that gives 1/3. Okay, sine inverse of 3x over 4 and the constant c, and you're done. Okay, so be a little bit careful about this part, but otherwise it's a nice problem and it's very popular for application if you want to continue now taking calculus 2 and calculus 3. So this is all we expect you to be able to do for us for this type of problems. Okay, to recognize it, we are not going to do something straightforward 1 minus x squared. No, we are not going to say it. So this is, there is one interesting for calculus 2. I'm not going to test you on that. I give you that one at the end. But otherwise, we are not going to have anything else. There are some other you can do for these type of problems. There are a group that we have to use something like, we call it completing the square method. But they can be done, you know, in calculus 2. But knowing the general one would be fine. Okay, any question? Let me just give one more. That's sometimes a kind of uncomfortable one. So that I'm going to give you this one. Don't be surprised. For example, if you want to take this, if you have the dx over radical 3 minus x squared. You see? Again, it's a sine inverse type because of the square root of, but this is not the one. You have to normalize this one. You see, this is x squared, so you don't know to do the substitution. So the solution quickly for this one is going to be, that's going to be a dx radical 3 minus x squared. So you realize that your a squared is 3. You see, remember this is a squared. So your a would be radical 3. Write it down as a rad 3 as well. We don't change it to the decimal, nothing. Okay, so your formula was 1 over a, it's going to be 1 over radical 3. Sine inverse of x over radical 2. X over radical 2 plus c, and be done. You can do rationalize, you can rationalize this one, but we don't usually rationalize the inside. We just leave it as is. Sine inverse of x over radical 3 is fine. Okay, so don't be surprised. We usually, you know, try to give you something nice. It's going to be all perfect squares. But if it's not going to be perfect square, not a big deal. Not a big deal, but you know, you can change this one if you like. I'm not going to be marked on, but don't do anything to inside one. It's kind of angle, or you know, just a number that we needed, and we keep it as is. So this is all we can say about this type of function for calculus 1. But there is one section, calculus 2, that take care of everything. Okay, any question? Because of we are not going to use the cosine inverse, or we are not going to question your cosine inverse, because you know from your previous course again that you see, look at this one. Y is not going to be good for us, especially for the integrations. You see, from the trig function, you have the following. Let me just go to the next page and explain this one too. So for the inverse cosine function, I just give a definition, but we are not going to question you on this. Okay, if you want to talk about inverse cosine function. Okay, the definition again from your pre-calculus course is, again, recall that the inverse inverse cosine function is going to be defined by, if you like. Again, you write it down as a y equal to the cosine inverse or arc cosine. Y equal to the cosine inverse of x, if and only if you just switch again. X is equal to the cosine of y. But the angle that you're going to use again for the purpose of calculus are going to be different. This is going to be true when where your y must be between 0 and pi, must be in the first or the second quadrant. And your x is going to be between -1 and 1 again. Okay, so in this case, the domain of this function is again closed interval of a -1 and 1. And the range of this function, range is going to be 0 and pi. Again, there are a different domain that you can consider for this type of function. The reason that they do this is calculus. You see, again, look at this one. So the cosine, we pick the y to be between 0 and 2 pi. So this is going to be sine, and this is going to be the cosine. So the y is here. Again, the reason that you pick this one is sine is always positive. So for the problems that in this part, if you will have to take the square root of the sine is, okay, square root of a sine, square of the y, it's always sine of y. And you don't need, again, you don't need a positive negative sign. So these are going to be used from time to time in calculus, but mostly for the sine inverse, not the cosine. And the reason is this one. Okay, you know that from it can be easily proved. Recall that there is a relationship between the sine inverse and the cosine inverse. This is it. Cosine inverse of x is equal to the pi half minus sine inverse of the x. You see? This can be easily proved. You know that if the sum of two angles happen to be phi half, let me say they are co-function, if you like. This means the sine of the, like 30 degrees and 60 degrees. In that case, the sine of the 30 is the same as the cosine of the 60. Cosine of the 60 is the same as the sine of the 30. We're just using that fact to prove this identity over here. So if you want to differentiate it, you don't have to worry about it. If you differentiate both sides, over here, you don't have it. So what's going to be the cosine inverse of x prime? Derivative of the pi half is 0, and the derivative of the sine inverse is just 1 over radical 1 minus x squared. So derivative of a cosine inverse is simply -1 over radical 1 minus x squared. Since it's very similar to the sine inverse, we don't usually look into this one. Because for purpose of the information in future, we usually going with integration, even if you want to integrate it. So because of this negative, you can write the result as a negative sine inverse or just go with the cosine inverse. So because of the similarity for the differentiation, you're not going to get anything new. So I'm not going to use it, cosine inverse of x. And it's true for even for calculus too. They usually just, if you know everything about the sine inverse, that would be enough. But if you want to collect the formula for yourself, this is going to be the case. Okay, so you're not going to have any question on the cosine inverse because you can express it in terms of the sine inverse. So it's not going to be a big deal. Okay, so this is going to be inverse of the cosine function. Any question? Now the big one for calculus, the most favorite one. The most favorite inverse function for calculus or calculus 2 is tangent. Okay, you get such a different possibilities for the tangent, and so popular because of the algebraically you see the domain. This function behave nicely, so make sure you know this one. So the two questions that you would get are going to be involve sine inverse and the tangent inverse only. So that's inverse. Okay, inverse tangent, inverse tangent function. Inverse tangent function. To get this one, again, it can be defined as we did it for the other ones. Okay. So just starting with the special domain, the domain is going to be the same as the domain of the sine inverse. So again, we recall that the inverse tangent function, the inverse tangent function is going to be defined by the following. There you are. Again, y equal to the arctan or tan inverse of x if and only if x is equal to the tan of y. Okay, that's the definition. The domain for the y is the same as for the tangent. For the sine, sorry. This is going to be, okay, the y must be between the pi half and the pi half. Okay, that's one. And the x is going to be free. X is anything between negative infinity and positive infinity. That's why this is popular, because of the domain, there is no restriction. Okay, so therefore, this is it. The domain of this function is going to be all real numbers. You see, and the range of this function, even the range, it's going to be negative pi half and the pi half. But even we can use the pi half and the pi half. So it's going to be negative pi half and the pi half. Okay, because of the domain, no restriction on the domain from negative into positive infinity, that gives us the nice function that we're going to have. Okay, now the derivative is the popular, so we can differentiate it. There you are. We do exactly the way we did it for the sine inverse. Note that if y is equal to the tan inverse of x, and if you are going to be interested in y prime, again, we have no information to operate here. We switch it and we differentiate it. Okay, again, we say that it's a note that. Now we start with the y equal to the tan inverse of x. We switch. If you switch that, give x equal to the tan of y. Differentiate with respect to the x. Lift of x would be 1. Lift of the tangent of y. Lift of a tangent, you know that lift of a tangent would be secant squared. But you have to multiply by y prime. These are all implicit differentiation. We're just applying the chain rule. So for get the y prime, so the y prime is equal to, okay, y prime is going to be equal to the 1 over secant square of y. But you would like to write everything in terms of the x. So what we are going to do is we just remind ourselves that we say, oh, but I know something. So what do you know? We know that the secant square of y is equal to the 1 plus tangent square of y. But the tangent is x. So that gives 1 plus x squared. So if you go back substitute, so y prime would be 1 over 1 plus x squared. So this means derivative of a tan inverse of x is going to be 1 over 1 plus x squared. Again, very popular formula. Because of this combination that you have, it's very popular to differentiate, very popular to integrate. So you will see it, from time to time. If you take calculus 2, it's going to be around for a long time. Tan inverse. Any concept that you have in calculus 2, they refer to the tan inverse somehow. So you have to know this one, carefully. Okay, so there you are. We make it official as a theorem. So of course, if it's going to be U type, you get U prime on the top. I'm going to write it as a theorem, and then we're done with the tan inverse. Okay, we discussed the secant inverse, but we usually don't question you on that one. Okay, but the sine inverse and the tangent are the one that we are going to have it, and those two questions that I talk about it. So 2 questions, 2 parts. Each part, for differentiation, you differentiate the sine inverse of x or sine inverse of u for one part, and the other part, again, you differentiate tan inverse of u or tan inverse of x. For the integration, the same thing, one from each. Okay, so very straightforward. And most of you did very well in the case of the integration on the test 3, that you have to study that carefully again. So you should be able to do it. So the theorem is going to be the following. The first one. So officially, the derivative of a tan inverse of x is going to be 1 over 1 plus x squared. Very easy to remember. The second part, of course, if it's going to be chain rule type, tan inverse of u, anything else, is going to be u prime over 1 plus u squared. You know that you differentiated, you multiply by u prime because of the chain rule. So this is going to be the case, and you can change it to the integral equivalently. And number 3, integral of 1 over 1 plus x squared dx easily would be tan inverse. You want to find a function whose derivative is 1 over 1 plus x squared. That function is tan inverse. It's going to be in u type. So that is going to be 1 over 1 plus u squared. The u, same thing, is going to be tan inverse of u plus c. But again, like the one that you did for the sine inverse, you see this, you need to start with the 1 plus 1 plus. It may not be 1. So what you have to do is, again, you have to pull out that. So that's the most general one. You get 1 over a squared plus u squared du. Remember, we did it for the sine inverse and we do it for the tangent. You see, you can do it if it's going to be 1 plus. So you have to factor out this a squared. If you factor it out, or divide the top and the bottom by a squared. So that would be u squared over a squared. So the result's going to be this: 1 over a tan inverse of u over a plus c. Remember, in the case of sine inverse, there is no 1 over a. Look at this one. Make sure that you do it all right. So in a case of the, you see, that's a similar formula for the sine inverse. Since the square root, that a would disappear when we do it. You see, look at this one. There is no 1 over a here. But for the tan inverse, because there is not a square root, this a would not be canceling out. So just make sure you remember it's 1 over a, and inverse of u over a. So this, the last one, is the most general formula that you need, and this is the most general formula for the derivative. And that you'll be able to take care of those two problems. Okay, that's a tan inverse. Any question? So let's give you one example, and then I'll give you a break, and we come back and we work on this and the similar problem from the review that we have. And I'll give you the formula for the secant inverse, but we are not going to question you on that one. Okay. So example, again, two types, exactly the same that you did for the sine inverse. Find the derivative of each function. Find the derivative. Okay, derivative of each function. Again, two types. One with the product. So it's very similar to one that we did. You see y equal to x to the fifth tan inverse of x. You see, this is a product of two functions. So remind yourself that you have to use the product rule. This is first. This is second. So we have to use the first, second. You see, the first times second plus second times first. The first second is straightforward. So because the derivative of x to the fifth is 5x to the fourth. Okay, 5x to the fourth times the tan inverse. Plus the second times first. Second first, if of a tan inverse. The of tan inverse is 1 over 1 plus x squared. Times the first one. You see, no chain rule is needed because this is x. So the solution, y prime equal to if of the first, 5x to the fourth times the second, tan inverse of x. That's if of the first times second plus second first. Second if of tan inverse, 1 over 1 plus x squared times the first. You cannot simplify it. The only thing that we did, we put this one on the top. So y prime equal to the 5x to the fourth tan inverse of x plus, plus simply x to the fifth over 1 plus x. Remember, you are done. Don't try to do something about it. No, you're not supposed to simplify it because you can't do it. So this would be the end of the problem quickly. Okay, so just recognizing that it's a product of two functions. So derivative of the first times second is straightforward. Second first, the formula, tan inverse, 1 over 1 plus x squared times the first, which is x to the fifth. Just put them together and then do that. Okay, so the differentiation that you get on the test are going to be this group and the exponential function and the ln function, like the one that you got on your quiz. If you check your quiz question number 1, you have all the differentiation regarding the ln function and the exponential function. You add this correction together. We are not going to give you anything from the past, okay? So don't worry about it. So this is a case 1 that we don't need a chain rules. Case 2, again, like the one that we did for the sine inverse, we need a little bit of chain rule. That's it. Function y equal to 3 tan inverse of x squared. You see, as soon as you get the x squared on the inside, so this considered to be u. So remind yourself that you have to use the definition. You have to use the formula for derivative of the tan inverse of u, which is the same thing. The bottom one would be 1 plus whatever it is squared but you have to pay for it, your prime on the top. Okay, this is the only difference between this and the other one. So y prime, and the first one, 3, is just a number. Derivative of a tan inverse. So get the fraction 1 plus u squared, 1 plus x squared squared. The top, pay for it, u prime. U prime, you see your u is 2x, your u is x squared. So your u prime is 2x. So the top would be 2x only. Okay, the bottom is always 1 plus whatever it's squared. The top u prime, derivative of the inside, like the sine and the cosine you did. Little bit of simplifications, monomials together, 3 times 2x, 6x. The bottom one is 1 plus, you see the old powers and the new powers, you multiply them together. So that give you x to the 4th, and you're done. Again, you can't do anything about it. This is the end of the problem. Any question? Now there is one popular for calculus 2. This is the one. This function is used quite a lot. Just make sure you are able to differentiate it for us. Tan inverse of the radical x. You see? So your u is radical x. So it's going to be u is radical x. You need the u prime. Remember, if the radical x is 1 over 2 radical x. Make sure you remember this. So simply y prime would be y prime tangent inverse is going to be 1 plus u squared radical x squared. On the top, u prime. Derivative of the radical x, 1 over 2 radical x. Okay, a little bit of simplification. It's 1 over 2 radical x on the top. Radical x squared would be x, going to be 1 plus x. Just bring that one down, or just multiply the first one by the reciprocal of the bottom. It's going to be 1 over 2 radical x times 1 plus x. Again, you're done. You don't expect to do anything about it. Even you don't have to multiply it inside. So that would be the end of the problem. Okay, so these are all the possibility for the derivative of the tan inverse. Give you a break, we come back and we do the integrations. Okay, integration is lots of fun in case of tan inverse, and I go over the one that we have from the, okay, on the review. So let's get all of them. Okay, so 2 questions from the things that I did so far. I give a definition for the derivative of the secant inverse. We can keep it for future. We are not going to question on that one. Okay, so it's 9:17, 15 minutes. We come back around 9:30, 32 if you like. And we continue and finish it. Okay, see you then. Okay, we give some examples on the integrating using the tan inverse function because it's very, very popular. Okay, so these are the possibilities. We just give you, a couple of popular one on this test. Okay, but I just list 5 types that we have in calculus 2. So there you are. Example. I just remind you the formula that, let's see, evaluate each integral. Evaluate each integral. On the test, we give you the hint. These are going to be separated from the question on the integral. We're going to ask you evaluate each integral, let's say using, just to remind you, using inverse trig functions, okay? Trigonometric functions. In this part, it's going to be mostly tan inverse. But this is the way you're going to see it on the test. So to do this, group that I'm going to list it for you. So these are the formula that you need. You need to know the following, that integral of du or dx, 1 plus u squared is simply tan inverse of u plus c. But if it's going to be anything other than 1, so du over a squared plus u squared. So it's going to be 1 over a tan inverse of u over a plus the constant c. This is the only formula that you need. I just write it down in terms of the u to give you more general term. Okay, type 1. Type 1 integral of dx, okay, dx over 4 plus x squared. That's a type 1. You see, this is x squared, so that's fine. But this is not going to be 1, it's a. So we have to use the second formula. You don't need any u substitution because it's already x. So this is the way you're going to take care of it. It's very easy to identify that's a tan inverse. So integral of a tan x plus 4 plus x squared. Remind yourself, your a squared is 4. Take the square root, your a is 2. That's just for your information. The formula 1 over a, 1/2 tan inverse of u x over 2 plus the constant c, and you're done. Just compare them together, you get the result. No simplification is possible, and then this is the end of the problem. Any question? That's a type 1. You don't need any u substitution. Type 2. Type 2 is going to be dx. Okay, dx, suppose this is 4 plus 9x squared, you see? So first thing to do is this is 9x squared, is not x squared. So you have to change this one into the u here. So the first thing to do, you have to change this one into the sign kind of du over 4 plus u squared. Then you'll be able to do it. Okay, so you need a little bit of a substitution, a mini substitution, we call it. So you rewrite it. It's a dx over 4 plus 3x all squared. So do your mini substitution to change this one into the u squared. So you take your u to be 3x. Your du would be derivative 3dx. You find the dx. The dx is the du over 3. Go back, substitute, change this one into the a squared plus u squared. Okay, there you are. So the integral of a dx, 4 plus 3x squared is equal to the integral of dx. What's a dx? Is du over 3 over 4 plus u squared. Nothing to be simplified. 1/3 an extra term, extra coefficients, put it out. So that gives it du over 4 plus u squared. So you have to do the u substitution to get it to the original formula. Okay, now from on, a squared is 4, so this is going to be equal to, remind yourself, a squared is 4, so your a is 2, and you're going to use this formula. You already got the 1/3 here, 1/3 times the formula, 1 over a, 1/2, tan inverse of u over a, u half, plus the constant c. You multiply and replace the u by 3x. So the final answer is 1/6 tan inverse. Okay, it's going to be 1/6 tan inverse of u. What is u? U is 3x. 3x over 2 plus the constant c. That would be the final answer. Okay, this is the kind of most general problem that you have when you're dealing with the tan inverse. Any question? So this is the 1, 2. Usually I question you on only 1 and 2, but if you want to see further for calculus 2, this next one is used a couple of times in calculus. Okay, in calculus 2, and this is it. You have a 2x plus 1 over 1 plus x squared dx. It's a very popular problem. Okay. Let's see how we're going to handle this. You see, the bottom one is 1 plus x squared. It's a kind of tangent inverse type. But the tangent inverse, the top must be 1 only. It's not 1. It's a 2x plus 1. So what you can do is you can separate it. So the solution is going to be, you separate it as, this is, that's the original one. You separate it as 2x over 1 plus x squared plus 1 over 1 plus x squared. You see this one? Now separate it as 2 integral. That will give you 2x on the top. And that would be 1 plus x squared dx. Plus, the top would be 1. This is going to be 1 plus x squared dx. You see? The second one is just tan inverse. What is the first one? You know that the first one is a rational function. There is no parenthesis here. So if you take this one to be u, remember, you have to check to see if the u prime is on the top. U prime is 2x, which is on the top. You know that u prime u is the derivative of the ln u. So the first one would be ln of the absolute value of 1 plus x squared. The second one would be tan inverse of x plus c. You don't need the absolute value here. So you prove that the integral of a 2x plus 1 over 1 plus x squared dx is simply ln of 1 plus x squared plus tan inverse of x plus c. You see, if you intend to take calculus 2, this problem would be it would be around quite a lot. And that give you a little bit more insight, these type of problems. And different techniques that we use. Techniques of integration is going to be mostly done in calculus 2, just for your information. Okay. So this is another one. Then again, the number 4 and the number 5 for future. You see, look at this one. Dx over 1 plus x plus 2 all squared. Look at this one. Again, you see this type of problems in calculus 2. You see, if you think about x plus 2 as u, this is simply 1 over 1 plus u squared, which is tan inverse. but it's usually tan inverse of x or tan inverse of u, which is tan inverse of x plus 2. You see a little bit of u substitution for this one, just to see the future. U is x plus 2. If you get the du, derivative of x plus 2 with just 1. So they give 1 times dx. So we get the dx and the du are the same. So if you rewrite this integral, that's a dx over 1 plus x plus 2 squared. Dx and the du are the same. And this would be 1 plus u squared. You know that, it's a tan inverse. Tan inverse of u. But what is u? X plus 2. Tan inverse of u plus c. So this would be tan inverse of x plus 2 plus c. And then you that. So these are going to be future. Maybe we're going to operate. And we don't do the substitution. We say, really, this is it. If I take u to be x plus 2, u prime is 1. So I have 1 over 1 plus u squared. So that gives you the tan inverse. Okay, again, this is the way you are going to operate it. And why we are interested in tangent inverse, because of this next problem. Look at this the next one. Again, for future, you have it in your assignments, in your book. But that would be too much. In calculus 2, there is one section that you take care of this. So there is a couple of more complicated integral. When you want to do it, you end up with this one. If you need more or if you like more. Again, we are not going to give you this type of question on the test. Look at this. You see it's a rational function. Of course, you need your prime on the top. It's a fixed number on the top. So you cannot use the substitution type for this one. What we do for this type of fraction in calculus 2 is we look at the denominator. If this denominator is factorable, we factor it. We factor it and we separate this fraction into 2 easy fractions, and then we can do it. But the difficulty is sometimes that denominator is not factorable, like this one. You cannot factor it. If you cannot factor it, you have to use a method from your algebra course. We call it completing the square method. We change this one into the form of a squared plus u squared. Then we can do it by the tan inverse. Just for your information and just a little bit of what you need in future. Okay, you cannot factor it because you cannot find 2 numbers whose product is 13 and the sum is 6. If you cannot factor it, you are going to use the idea of completing the square from algebra to pull out a square. You see this is going to be x squared plus 6x plus 13. Completing a square is, you see, you get this coefficient. I'm going to use this formula. A plus b squared is a squared plus 2ab plus b squared. Remember in algebra. So if you pull the b squared to the other side, that gives you a squared plus 2ab is equal to the a plus b squared minus b squared. You see, or even you can start with the negative here. It doesn't matter. This would be negative, okay. That would be negative, doesn't matter. You see, this is the type that you are going to be interested in this form to be able to do the problem for us over here. So the question is going to be, you see, this is twice of the first times second. You divide this one by 2. That gives you 3. It's the way you are going to make this a square. So it's going to be equal to the you write x plus 3 all squared. You see, if you write x plus 3 all squared, you square of the first one, x squared. Twice of the first times second, 2 times 3, 6x, but plus 9. You don't have any 9 here. So what you have to do, you have to subtract the 9 and the 13. You have done this by solving the quadratic equation in algebra. So easy to do. You divide this coefficient by 2, that gives you 3. Write your square, x plus 3 all squared. Now look at it. That gives you x squared. 2 times first times second, 6x plus 9. You don't have a plus 9 here. So you subtract the 9 to make it, make it even. Now, if you simplify it, that gives you x plus 3 all squared, but plus 4. So this integral can be rewritten if you like. This is going to be dx. And this would be 4 plus x plus 3 all squared. And you can do it with the tan inverse now. Because if you take this one to be u, you see it's like 1 over 4 plus u squared. You see, if you take it to be u would be x plus 3. Then the du would be simply dx. If you go back and substitute, that's a dx over 4 plus x plus 3 squared. So that would change to the du 4 plus u squared. You see? But this means a squared is 4. So your a is 2. So that you 1/2 tan inverse of u half plus c. But u was what? X plus 3. So that gives you 1/2 tangent inverse of u plus x plus 3 divided by 2 plus the constant c. So this is the way you operate for this type of integration. And that's the important role of the tan inverse for calculus 2. Or this type of function is going to be 1/2 tan inverse of x plus 3 over 2. So just give you a taste for what can you do with the tan inverse for future. It's important application. If you want to integrate the rational function in calculus 2, this would be one of your examples. Okay, but we are not going to give you these type of problems in this course. Just if you take calculus 3, you see, then you have to, just for information, you are going to be doing this problem, and this is where you use it. You see this one? And that would be x squared plus 4. Okay, x squared plus 4 times x squared plus 3. You see, in calculus 2, if you want to do this problem, which is very important problem. So what you do, you break it in two parts. When you break it 2 parts, so the denominator would be of the form of x squared plus 4 and x squared plus 3. Then you can do, you can do the tangent inverse one. But just to remind you. So you have, you should know the type that I did over here, just type number 1 and number 2. Okay, the rest we just give you for your information. It's good for you to study this. Okay, but we give you something straightforward, so nothing to worry about. Okay, so this is it. This is the tan inverse. Any question? Secant, cosine, I talk about it, but just give you a remark for the secant inverse, but we are not going to question that. I just give you the formula, and the derivative is popular, but not the integral. So what's going to be the inverse? Inverse secant function. Secant function. I'll just give you the formula for the derivative because I want to go over the one that you have on your practice one. This is it, the derivative of a secant inverse. You must know the derivative is going to be simply 1 over x radical. It's absolute value of x, but we go with the positive. X squared minus 1. We assume that x positive. That's derivative. And if it's going to be in terms of the u, so simply it's going to be the same thing, but u prime on the top. So that gives you u prime, and that's going to be u radical u squared minus 1. Okay, the combination of the derivative is not as nice as the sine inverse and the tangent inverse, but the derivative is important. We use it quite a lot in calculus 2. Okay, just one example on this one, and we finish it. No integral or the secant inverse, but just a couple of differentiation as we did it for the other. But I think the question on your test is tan inverse and the sine inverse. But bring this formula also to your test in case you need it. So, but I don't think so. Find the derivative of each function. The derivative of each function. As we did it for the other, something with the product first. X squared secant inverse of x. Again, derivative of the first times second first. For the second first, we just use this one and we differentiate, okay? So that's the first, and that's the second. So f prime of x is equal to derivative of the first function, 2x times secant inverse, done. Less derivative of a secant of x, that's it, secant of x, 1 x radical x squared minus 1 times x squared times x squared. You can only simplify these two. So the f prime of x is equal to the 2x secant inverse of x plus x on the top, radical x squared minus 1 down the bottom, and you're done. Again, you cannot simplify it. You cannot do anything about it. This is the end of the problem. The only thing that you can do is this part. Okay, so you know the formula and just substitute. Question? Something with the chain rule? Gx equal to chain rule. 2 times secant inverse of x squared. Okay, that would be the chain rule type. So the derivative, g prime of x, 2 is a number. So we just keep it. 2 as 2. If you have a secant inverse times 1, whatever is here, you bring it down, x squared, a square root of, whatever here is squared, minus 1, but you have to multiply by u prime. U prime derivative of x squared, which is a 2x. I'm just using this formula. You see the u is x squared. So that's u. Radical u is squared, x squared minus 1 times u prime, which is a 2x. So we can simplify a little bit. G prime would be equal to, so this x and x would cancel out. There is a 2 times 2, 4. And the bottom one would be x radical x squared, which is x to the 4th minus 1. So that gives you the final answer. So that's the best you can do. Okay, so this is all you need. You don't need the cosecant because it's like the one that you did for the sine. Cosecant of the inverse is pi half minus secant inverse. So you need only sine, tangent, and the secant. Sine, tangent, secant for calculus. The rest you don't need it. Okay, that's it. This is all the section, all the inverse trigonometric function that we need. As I'm going to talk about it, we are going to have 2 questions on this one. So I'm going to do the one that we have on the review regarding these 2 functions, and I'll give you an idea of the topics that we're going to cover. Okay, so we did cover everything we need. Okay, so 13 question on the final from the topics on the review. So as I talk about it, let's just bring the review, explain it. So this is it. Let's try to share it. Okay, can you see the review?
Yes.
Okay, very good. So I'm going to explain the topics, and it's going to be on the final. Okay, one by one. So it's going to be 13 questions, and you are going to answer, okay, 12. So the first topic is this one, mean value theorem. Remember, you did it on test, I think that was test 3, or maybe test 2, just check it. So we are going to give one of these function, and we ask to see if the mean value theorem, remember, NVT, it can be applied. You know that. You just check this function must be continuous, differentiable. Then you form f of b minus f of a over b minus a equal to f prime of c. Just solve for c. Okay, we go over it. This. I give you the solution of one of them later tomorrow. So that would be question number 1. Then differentiation. We are going to have 2 groups of differentiation. The first one is the one that we did just today. Inverse trigonometric function. You see, these are going to be the one. There are 3 functions, but we give it 2 of these 3. Okay, this is derivative of the sine inverse and derivative of the tangent inverse. So bring the formula that I talk about it for the derivative of the sine, tangent, and the secant. But 2 of these 3 would be given to you, okay? So that would be your first question on the derivative. Then your second question on the derivative is going to be related to the exponential function and the ln function. This is from your quiz number 4. We already give you all these solutions when we discuss the solution of the quiz 4. So you have all of them. I'll give you the solution to the number 2, but for number 3, you already got all of them. So that would be the question on the derivative of the function. Okay, then application of the derivative of the function, optimization problem, as is on your quiz. We give you one that we ask you to find the maximum and the minimum. So you can use the first derivative test or the second derivative test. This is number 4. We give you all of them. You have all of them in your practice quiz number 4. And you have 2 of these on your quiz today. So study those again. So you have the solution of the number 4 and the number 5. So we give you one from exponential function, one ln function. We are not going to give it an inverse, okay? So check the solution of this number 4 and 5 on your, your practice quiz. Then integration by substitution. These are all that we did. Okay, if you check practice quiz number 4, you have the solution of all of them. There are 6 type of function. We put them together. So you get 2-3 questions of these, like on the quiz and like on your practice test number 3. So you know that it's a substitution method. We have 4 types. This is the type that you remove the radical. This is the rational function. You check when there is any power, you move it up. When there is no power, you just do it by the natural log function. We give you this, remember the sine, cosine, tangent, and you have one of them already on your quiz 4. So this is going to be the question on the So on number 6, just check all the solution that you have. Get 2 to 3 questions from number 6. Then ordinary integral integrations. This is where you don't need a substitution method, okay? So we give a couple of them, one question. So it's going to be mostly the kind of definite integral rather than this one. But study this. You have the solution. Check your quiz number 4 again. And yes, we have all the quiz in there. Practice quiz number 4 or practice test number 3. And of course, integral function. This is where you differentiate integral. You drop the integral, replace the t by x. You did on test 3. Some of you missed it, but most of you did all right. We are going to be interested in this type for this number 8. We did one in your test, and we are going to repeat it again. So to be able to find the value of the function, derivative of the function, and the second derivative. So check this one. You already got the solutions. So we give it 1. A definite integral, when there is a number here, 0 to 1, you have to use the intermediate fundamental of calculus. You did on test 3. We repeat it again. In 2 cases, the one that you need substitution method like this one, and you did have one on the test, or the one that you don't need a substitution method. So it's going to be 1 question, 2 parts. Average value, number 10 and 11. We are going to be interested in the application types. So I did the number 11. You have 1 on the quiz. Check it. Okay, so from the 10 and the 11, we give you 1 average value, just, to make sure you know the formula for the average value. So it should be find. And now the new one is number 12 over here. This is integration by inverse trigonometric function, the one that did today. There are a couple of 4 possibilities. We put them together and we give you 2 of these. Okay, part 1, part 2. One of them would be related to the sine inverse. The other one would be related to the, one to the sine inverse, and the other one into the to the tangent inverse. Okay, so 1 question on this this problem. Okay, and of course number 13 is the L'Hopital rule or Hospital rule. Hospital rule, just 1 question, 2 parts. One of them would be the one that you get 0, 0. This is 0, 0, infinity, infinity, and this 0 times infinity. Again, you have a solution of this. Okay, check your practice quiz number 4 for the solutions. So you already got the solution of all of them. You have to check the practice quiz number 4 and some of them on practice test number 3. There are just a couple of them that you don't have the solutions. It's going to be number 12. You don't have it. I try to give you some of them or maybe all of them today. And the other one is inverse trigonometric function, which is going to be number 2. Okay, you have the solution already. So start working on it. No surprise, all of them are going to be from these topics. Okay, so study this and then you'll be fine. You don't need mostly your test 1 or test 2. It's all test 3, quiz 4, and the one that I discussed, okay, the one that I discussed today, that would make the final. Okay, so I'm going to go over that that inverse trigonometric function that we have. I just double check here. This is going to be for the integrations. This is number 12. This is going to be the one that I'm going to discuss, the number 12 for you. And I do the derivative of the function. Okay, I just want to make sure because I have 2 different reviews on my notes. I want to make sure to get you there. Okay, so we go with the number 2 first. We do number 2, derivative of inverse function, and number 12, which is going to be that integration. Okay, so that is the plan for your test. Okay, so it can be study carefully this, and you have all the formulas, and you'll be fine. People usually get very, very good grade on the final. Okay.
Professor, I have a
Yes.
question. So are we still allowed to bring the formula sheet?
Yes, but if I see any example directly, I don't grade your final. Yes, formula sheet, 2 pages, two-sided. Double-sided, only formula. You cannot bring, I saw some of people, they bring these examples that they did on the review on and their formula sheet. Yes, a formula sheet, double-sided, you can write any formula that I call it formula, especially if you did quite a lot today. But if there's going to be any example, okay, you cannot put this example in your formula sheet. Otherwise, we don't grade your final. Okay, any more question regarding final? So take the final, I will grade it. I post your result on Friday, okay? And just check your result. If you have any question, just let me know right away, because there is a deadline for submitting the grade. So I have to grade it and submit it on Friday. So if you have anything, about it, you just email me on Friday when when I post your grade. And the grade would be posted on the canvas. You have the percentage, and then you are going to have another column. That column would be your grade. I don't go with the minus and plus. So your grade is going to be just the kind of the actual one that we have. Okay. So let's try to see if we can do some of these, and I go over again some of the problems tomorrow. The one that we didn't do, okay. So this is going to be the final review, new part. Otherwise, you have all the other one. So that's going to be final review. Okay, this is final review and question number 2. You get one. And number 2 is 2 parts. One of them would be derivative of it's going to be sine inverse and the tan inverse most of the time, and we put all of them here and would be very, very similar. So find the derivative of each function. Find the derivative. Okay, the derivative of each function. Let's say it's going to be a straightforward part 1. Part 1, y equal to, okay, x to the 4th sine inverse of the 3x. That's it. You have to apply the product rule. You say derivative of the first, derivative of the first times second, and derivative of the second times first. Okay, so this is it, solution. Y prime equal to derivative of the first one, 4x cubed, times the second function, sine inverse of the 3x, plus derivative of the second one, derivative of the sine inverse. Derivative of sine inverse is 1 square root of 1 minus whatever it is, a square. Most of the time it's x, but it's a 3x. So it's a 3x squared. Since it's a 3x squared, you have to multiply by u prime, which is 3. That's the derivative of the second one. Okay, if it's happened to be x, the top is just 1, because u prime is 1. But in this case, it was 3x. Okay, times it by the first one, times it by the first one, x to the 4. The only thing that you do is this 3x squared. So y prime equal to 4x cubed sine inverse of the 3x, and this is going to be plus 3x to the 4th. Okay, the square root of 1 minus 9x squared, and then you that. No further simplification is possible, and then you that. Any question? So if this is going to be sine inverse of x only, there is not going to be any 3 here. So that give 1 minus x squared. Just bring the formula and just check it, and then do that. That's the case with the sine inverse. There are 3 cases, but they give you 2 of these 3. Okay, the case 2. The case 2 is g of x. This is the one that I did. G of x equal to the tan inverse of the radical x. That's it. It's like tan inverse of u. Just remind yourself, the formula that you need is this one. Derivative of tan inverse of u prime, 1 plus u squared. That's the formula that you need. So g prime is equal to, do the bottom one first, 1 plus whatever it is, a square, radical x squared. The top u prime derivative of radical x, 1 over 2 radical x. Simplification would be just the bottom one, 1 over 2 radical x. This would be 1 plus x. Just bring the 2 radical x, 1 over 2 radical x times 1 plus x, and then you do that. Remember, you don't have to go on. It's just the final answer. Any question? So you need the formula for the tan inverse, sine inverse. And the last one is secant f of x equal to 2x secant inverse of x. Is a secant inverse of x, you just need the derivative of a secant inverse, you see. The derivative of a secant inverse is 1 over x radical x squared minus 1. But it's a product of two functions again. Derivative of the first times second first. So f prime of x is equal to derivative of the first one, derivative of 2x is 2 times the second function plus derivative of a second function times the first one. Derivative of a second function is a secant function, so it's going to be 1x radical x squared minus 1 times it by the first 2x. So this x and x would cancel out. So f prime of x is equal to f prime of x is equal to the 2 secant inverse of x plus 2 over the square root of x squared minus 1. Again, no simplification is necessary, okay? So don't try anything. This would be the end of the problem. Any question? So that's a question on the derivative of the function. So it's a 3 types of function, but we give it 2. It's going to be 1 question, 2 parts. One of them is probably the one that you have to use the product rule and the inverse function. The other one is you don't need a product rule, like you see the middle one that we did. This is the one with the product, and this is the one without product, and then you that. Okay, so that would be a question on the derivative of the inverse function. Any question? Your second question on the inverse function is going to be integration. Again, 1 question, 2 parts. And this is question number 12. Okay, question number 12 on the review. We give you the hint, differentiate using the inverse function. Sorry, integrate. So find the h integral. We give you the hint using inverse trigonometric function. Metric functions. We need only 2 formula for this group. And these are the general form of the formula that you need. The first one is this one, integral of du over square root of a square minus u square is, that's sine inverse of u over a plus c. That's the first one. And the second one is this one, du over a squared plus u squared. This simply is 1 over a, tan inverse of u over a plus c. That's it. You don't need anything else. If you want, just a simple one is when a is equal to 1. So I just write it down in terms of the a. So, it's easy for you to memorize it. Okay, 2 questions, just compare to see which one is it, and then you can use it. And these are all the possibilities that you can have. The first one, integral of 1 over 9 plus x squared dx. It's of this type. Let's see it. This is x squared, so it's like u is equal to the x. No substitution is needed. So simply a squared is 9, so your a is 3. That's it. 1/3 tan inverse of x over 3 plus c, and you're done. Just recognizing the formula, and then, so this is it. 1 over 9 plus x squared dx is equal to, remind yourself, this is just for information, your a squared is 9. So your a is 3. So it's a 1/3 tan inverse of x third plus c. Do that. Okay. Any question? Case 2 of this, you need a mini substitution if you like to get it. And the case 2 is this one. 1 over 3 plus 4x squared. I rewrite it in this form. Again, it's of this category. But, it's not x squared, if you like, it's a 4x squared. So you have to do the mini substitution. So u squared is 4x squared. If you take the square root, u would be 2x. So you do the substitution to make it into this form, and then you'll be able to do it. Okay, so that's extra. This is only x squared, it's like u squared. But this is 4x squared. So it's not x squared, something else. So the mini substitution is going to be, you think about it, rewrite it as 1 over 3 plus 2x all squared. So do the mini substitution to make this one to the u. So we take u to be 2x. Your du would be 2x dx. And your dx would be du over 2x. Sorry, this would be just 2. Derivative of a 2x is just 2. So it's going to be 2 dx. Dx would be du over 2. Go back, substitute, and then it's ready. So rewrite it. It's going to be the case, both of them, for the tan and the tan inverse and the sine inverse, that in the second case, you have to do a mini substitution. 1, 3. This is a u squared. So what's your dx? Dx is du over 2. So the extra coefficient is going to be 1/2. Take out the 1/2. So you take out the 1/2, that gives you du over 3 plus u squared. Okay, so you switch it into the format of your theorem, you see. Your a squared is 3, so your a would be radical 3. Don't be surprised, radical 3, fine. So it's going to be equal to, so we get a squared equal to 3. This is just for your information. A would be radical 3. So we already got the 1/2. The formula is, you see, 1 over a. A is radical 3, so it would be 1/2, 1 over radical 3, tan inverse of u over radical 3 plus the constant c. You multiply inside, you don't need to rationalize it. 1 over 2 radical 3. Tan inverse of u over radical 3. Let's see. And you have to go back and substitute for u. So that you 1 over 2 radical 3. Tan inverse of u. U is 2x. 2x over radical 3 plus the constant c. So that's a kind of most general one that you have in dealing with the dealing with the tan inverse. Any question? There's the 2 categories. It's 2 categories for the tan and the 2 categories for the sine inverse. You will get each of them. Okay, that's it. So it would be the same for the sine inverse. I go with the D. C is the one that I did on that just a lecture note. I just want to give you the D so that you have them to practice. So this is the other possibilities. 1 question, 2 cases. You're done with the first. What's the second one? Integral of 1 over radical 4 minus x squared. It's a sine inverse type. You see, this is the formula that you're going to use. 1 over radical a squared minus x squared dx. It's a sine inverse. It's going to be sine inverse of x over a plus c. Remember, in case of a tangent, you have 1 over a, but in the case of the sine inverse, you don't. So it's a straightforward. Integral of 1 over radical 4 minus x squared dx. Your a squared is 4. So a is 2. So that gives you sine inverse of x over 2 plus the constant c, and then you're done. So it's going to be a straightforward. And the last case, again, it's like the one that we did for the tangent. You see, it must be x squared or u squared. It's not. So you have to do the substitution as you did it for the tan inverse. So there you are, rewrite it. 1, 2 minus 3x squared. Do your mini substitution, u equal to the 3x. Again, du is 3 dx. So the dx is du over 3. Go back, substitute, that give you sine inverse. So integral of 1, 2 minus 3x all squared dx would be 1, 2 minus u squared now. What's the dx? Du over 3. Well, the 1/3, the leftover is just sine inverse. So it's going to be 1/3 integral of 2 minus u squared du. You see, a squared is a radical. A squared is 2, so a would be radical 2. A squared is 2, so a is rad 2. So the final answer, 1/3 sine inverse. Remember, there is no 1 over a. Sine inverse of u over a. Let's see. The substitute for u. So that gives you sine inverse of u. What is u? 3x. 3x over radical 2 plus c. That would be the final answer. Okay, so it's a 2 action. One of them is straightforward. The other one you have to use u substitution. There were 4 possibilities. We give you 2. One of these for the sine inverse, one for the tangent inverse, and that would be regarding the integral of the inverse, they're going to be the function. There's not going to be any secant inverse. That's it. Any question? So try to finish your quiz. I'll go over that quiz tomorrow because 6 similar question of the quiz would be given to. So I've already given you 2 here and the 6 from the quiz, 2 and 6, 8. And all the other 4 are going to be, as I talk about it, is mostly substitution method and the definite integral from test 3. So you don't need the test 1 and the test 2 for the final. Okay, that's it. Just let me know if you have any question. Otherwise, good luck. Study the one that we already talked about it, and you'll be fine really for the couple of days that we have. Okay, I have to go on my next class. If you have any question, just email me. I'll be available on Zoom 5 to 6. Okay, if you need anything, you have to email me first, then open up the Zoom and you can come and we have any question. I'm happy to answer. Okay, have a good one and good luck. Bye-bye.